Thank you for joining me to watch the video on Einstein's A and B coefficients, emission and absorption rate of single atoms. So this of course is a lecture video regarding the laser physics course. And now in this video we will be understanding the mathematics, how we can understand how much laser light is being absorbed into the laser medium, and then subsequently also how strongly it will emit light. So essentially it will give us a quantitative means of understanding what happens when light is shown into the laser medium. So let's get then started right away. I have lots to discuss to you today, this lecture. So as we already learned previously, we are dealing with fundamental few interactions when light is hitting a material. So essentially what can happen is that we can have absorption, we can have stimulated emission and spontaneous emission. And the system we are considering here is really a two-level system. We don't really need to be concerned about other systems right now. And these interactions really are governed by Einstein's A and B coefficients, named like this due to the fact that Einstein made the original pioneering contributions to calculate these coefficients. So the B coefficient governs the rate of absorption or stimulated emission. In a way, these are inverse processes, so their strength is equal. So if you look at the rate of absorption coefficient, that equals to the rate of rate of stimulated emission within the material, and that basically can be written using the Einstein's B coefficient, and then in radiation energy density associated with the medium. So essentially, how much of light is impinging into the material, and also what kind of thermal environment do we have surrounding or inside the material. So here, this W term here inside the brackets is the radiative energy density, essentially consisting of the energy carried by the incident electromagnetic field, that is our pump, and then of the thermal energy due to the fact that actually the atom or the bunch of atoms, the gain medium is inside an environment at a finite temperature T, and that gives rise to also this kind of like thermal ambient electrodynamic field environment in which the atoms are residing. Okay. The rate of absorption, and let's now first start looking into the B coefficient that concerns the absorption and stimulated emission. The process is given by that we want to calculate the absorption rate, the W-abs value, and that's basically, if you look how it's being defined, it's the absorption probability divided by a unit time. So now if you look more mathematically, it's essentially a time derivative of the modulo square of the coefficient. What is for the electron to be in the excited state. So essentially now we can approximate essentially a linear approximation of that time derivative, and this is the kind of like approximate equality we have for the case. So it depends on the inverse of time and then of the square modulus of the CE expansion coefficient. And this is equal to the Einstein's coefficient times the radiative energy density on inside the material. So let's now estimate the radiative energy density, and we need to relax our assumptions a little bit that we just made before. So mainly we relax the assumption that the transition is monochromatic at omega naught value of frequency. So essentially we are no longer considering a fact that the transition is just a delta peak given by this kind of like a delta function. In reality, all transitions really have a certain line width delta omega, and that's the case. What we want to do next, so that we want to generalize our treatment slightly so that we can consider more realistic materials. And in this case, we can really write for the amplitude squared of the electric field, so that that's equal to the 2 divided by epsilon naught, so the vacuum permittivity, and an integral over this radiative energy density over a range of frequencies. And slightly now we can rewrite the expansion term and the modulo square of that, so that this equals to 2 times E, the charge of an electron, times the transition dipole matrix element, GE, so essentially telling us how likely it is the electron to transition from the ground state to the excited state, and then divided by the vacuum permittivity and reduced Planck constant h bar. Now we integrate over a range of frequencies, and then we are integrating the radiative energy density and this kind of sinusoidal term that we discovered in the previous lectures. So this is basically now the kind of like generalization that in fact we don't have just a delta peak, but rather we need to integrate this kind of term over a range of frequencies. So this is basically a means to calculate then the expansion coefficient CE, telling us the rate of transition into the excited state or population within the excited state. So the XGE, like we used this kind of simplifying notation in the previous lecture already, that's the transition dipole matrix element. And now let's look into the math for a small values of t. So in the beginning of the process, for rate of absorption, we can really approximate that these sinusoidal terms here, sine squared times 1/2 times omega minus omega naught times t, divided by the omega minus omega naught in the squared terms. That's approximately t squared divided by 4. So in the kind of like beginning of the absorption or stimulated emission process, that's the kind of time dependence that we have. But usually we are not really interested in the kind of like short time intervals, but rather we are interested in the kind of like asymptotic behavior. How does the transition rate look like when kind of longer time has been accumulated? So let's consider for a larger or longer time values. And now we can integrate that the expansion coefficient modulo squared is of an integral over a given frequency values of this same sinusoidal term. I will just not label them and name them again. And this is approximately, if you do the math right, pi times t/2. And now plugging this into the previous term that we got for the expansion coefficient, that it roughly depends on this time derivative of CE is approximately looking like this. And that basically is equal to the Einstein's B coefficient times the radiative energy density. We see that the rate of absorption becomes really time independent. So this is basically like a plugging this guy, that's equal to this expansion term squared. So here t's cancel out, and we see that this rate of absorption is really time independent value when we are looking at the kind of longer time interval values. And this is the kind of like the main thing we wanted to see here. In addition, this transition dipole matrix element is averaged over all directions. So usually we are really concerning, for example, a kind of like a atomic media where the atoms can be residing in all different directions. So then the like a final value will be 1/3 times the dipole moment element concerning the transition from the ground state into the excited state. And now we can really like write the final expression for the Einstein's B coefficient. So B equals pi times E squared times the modulo square of this dipole moment divided by 3 times the vacuum permittivity times the h bar squared. So this is our Einstein's B coefficient now calculated, and that gives us a tool to estimate, for example, the rate of absorption into the medium or the rate of stimulated emission out from the medium. Now, with this result, we can really write the expression for the absorption and equally to the stimulated emission rate, that the rate of absorption is basically the B times the radiative energy density, and this is what we kind of discovered for the B previously, and this is the kind of equation that we have. So now we really see that the absorption rate, WABS, depends on A, the properties of the active medium through the Einstein's B coefficient, and C, of course, depends on the incident electromagnetic field through the radiative spectral energy density, this W term within the brackets. So that's what we have discovered so far. So that the kind of like absorption rate depends on both on the medium and of the incident electromagnetic field. And let's now hurry quickly or very like briefly into the calculation of the A coefficient. And that's, of course, concerning the spontaneous absorption. So this is a little bit more difficult to actually calculate because it really requires quantum electrodynamics to do it properly. And this is really beyond the scope of our course. So if you are really interested in seeing the calculation, please check, for example, this reference, The Quantum Theory of Light, section 1.5 by Loudon in his textbook. And the result, we just show how the result turns out to be. So the A coefficient is really basically defined as the inverse of the radiative time. And that's given by the h bar times omega naught to the power of 3 times g. So this is essentially a degeneracy parameter for the ground state. And then all of this divided by pi squared times the speed of light to the power of 3. And then GE, which is the degeneracy factor regarding the excited state. So essentially these G parameters here tell us a possibility that we might have several energy states within the same energy interval, but nevertheless they would be different states. And then we multiply this with the Einstein's B coefficient. So really we see that the A and B coefficients are interrelated with this kind of equation. So if we cannot calculate the B coefficient, then certainly we can calculate the A coefficient and so forth. So, like I said, these G parameters are the degeneracy parameters, and tau R is the radiative lifetime of the excited state. So essentially, that's a kind of good way to understand what is the kind of physical meaning of this Einstein's A coefficient. So it's really the inverse of the radiative lifetime of the excited state. So essentially kind of like how quickly or how slowly the system relaxes. So this was my lecture regarding the Einstein's A and B coefficients, showing how this calculation goes or the derivation goes. And these are really the parameters that tell us how we can quantitatively understand how easily, how difficult it is to kind of have the material, our gain medium, to absorb light, and consequently how easily it is to get stimulated emission going on within that medium. Thank you for my time and for your time, and please stay tuned regarding the next lectures on our course on laser physics. So thanks and bye-bye.